Good afternoon, folks. This is Armand Pantalone, the Chief Technology Officer for Giga-tronics, in yet another installment of our TEmS Talks. We're talking you through a whole series of our product lines in the thread emulation system world, and one of the products we want to highlight today is a product that we call PDW2RF. And what that stands for is Pulse Descriptor Word to RF creation. And we're going to show you some of the features today. There's a lot of things that this product does, so we'll probably break this series of talks into maybe 3 different videos. But tonight, that video we want to show you is the most important feature. And what we want to show you is this product's ability to take a Pulse Descriptor Word interface and create RF on our own product line, regardless of where the Pulse Descriptor Words came from originally. So for us to show you the ability of our product PDW2RF to create RF from someone's Pulse Descriptor Word interface, we're going to first show you the ability to do it with our own proprietary interface. As you've seen before, this is a complex scenario from the Giga-tronics proprietary RF thread emulation system, or TEmS. And what we're going to do is grab the actual Pulse Descriptor Word binary file that's created during the real-time execution of this RF thread emulator to our own proprietary PDW interface, and we're going to bring that file over to the product that is the PDW2RF, and we're going to show you how to create RF with a completely different set of hardware. The reason to do that is because we want to be able to show the ability of us to create RF from someone else's PDW interface. If you've seen our series of TEmS Talks before, you're probably very familiar with this complex scenario. This is a number of airborne targets flying through a canyon with some ground-based missile defense, air missile defense radars. While this is a very realistic, complex scenario, it's very hard to show you that we're properly creating the RF in this scenario. So we're actually going to change from this scenario to something more simple that is very easy for us to prove that we're properly creating the RF from another scenario. So give me one moment. We're going to call up a simpler scenario of 4 emitters. And what we're going to do is show you the 4 different RF channels with 4 different pulse parameters, and how we can faithfully recreate that on our PDW2RF hardware across the lab on a completely different set of hardware. So we're going to run this. You can see the 4 pulses in real time. Very boring, but different pulse widths, 4 different modulations. The same period, overlapping in time, we'll be creating this. The reason for this boring scenario is to show you the modulations, the pulse widths, the PRIs, and all the other parameters are faithfully reproduced. And what you're going to see on this channel 1 is simply pulse CW with a set center frequency, pulse width, and PRI. Channel 2 in red is the same pulse width and PRI for every pulse, but it has 3 different linear frequency modulation chirp bandwidths, 5 megahertz, 10 megahertz, and 20 megahertz. The third is a binary phase shift keying code, and the 4th channel is a series of 4 different frequency shift keying pulse CWs at -5 megahertz, +5 megahertz, -10 megahertz, and +10 megahertz. Away from the normal center frequency of this RF thread emulator. So to accomplish that, we're going to switch on the ability of our Giga-tronics RF thread emulation system to actually collect a digital record of all the Pulse Descriptor Words created during the execution in real time of this scenario. It's just a shot of the hardware. And to do that, we're going to select the option for collecting Pulse Descriptor Words. And you can see on the GUI here that it's collecting Pulse Descriptor Words. And I'm going to execute the scenario and grab about maybe 10 seconds worth of it. So again, it's very boring because we're intentionally creating RF that we can easily identify on another piece of equipment what are the pulses in the train. So we're probably past the 10-second mark, so I'll stop collecting the Pulse Descriptor Words. And if you look at the time stamp on the computer, it's right now Thursday, October 6th at 7:53 p.m. So I'm going to pull up the file. This is the thread emulation system database that we're operating from. And right at 7:53 with today's timestamp, this particular PDW file, this binary file, is what we're going to carry over to the other machine and create this RF on a different piece of hardware. So we'll proceed by just copying it over on a USB stick, and we're going to sneaker net it across the lab. We're going to grab the file we just created by executing the Giga-tronics TEmS, copy it over to our USB stick, and then we're going to sneaker net it across the lab and copy it to the other PC that hosts the RF SoC card that we use the digital analog converters on, and our own proprietary software and firmware to translate this PDW interface to RF. We're going to create it, put it in that particular file at the 7:53 time frame. Okay, meet me on the other side of the lab. All right, so we're on the other end of the lab, and this piece of hardware is what we want to show you. This is just a PCIe backplane based PC that we're using for the design and development of this product. And embedded in this PC workstation is an RF system on a chip card, and it has 8 channels of A to D conversion and 8 channels of D to A conversion. So the digital analog converters are what we're going to utilize to create the RF from this PDW stream that we copied over. Right now it's running a file in the background, and we're going to copy over the file we just created from the thread emulation system on the other end of the lab. This 753 file we'll copy to the same folder that we're going to execute from. That's good. Okay, so we copied the file over via the USB stick to this other machine. We copied it to the directory we're going to use with the PDW2RF RF SoC card, and we're just going to load the file first, then we're going to run it. You can see right now it's not running any file right now. So we're just going to load the file on this particular folder, and it's the 10:06, 7:53 p.m. timestamp, and we're going to run. So what we're going to show you now is having captured the binary PDW file from the thread emulator on the other side of the lab, and we've loaded it into this machine, the PDW2RF RF SoC card. And unfortunately, we broke the third channel, the third DAC channel, so we'd only show you 3 of the 4 channels. We'll probably update this video series with a replacement video when we have the third DAC channel repaired. So we'll show you 3 of the 4 DAC channels. And remember, the 4 timing pulses had 4 different modulations on them. One was a pulse CW of the same pulse width and period as channel 2, but channel 2 had 3 linear FM chirps, 5 megahertz, 10 megahertz, and 20 megahertz. The third channel that we can't show you, unfortunately, because we broke the RF connector, on the back of the RF SoC card. That had the binary phase shift keying modulation, And the fourth channel, if you remember, had the 4 frequency shift keys of -5 megahertz, +5 megahertz, -10 megahertz, and +10 megahertz around the center. So we'll show you all that being recreated on a completely different piece of hardware than the RF thread emulator that the PDW train was actually created on. So we'll start to show you not only the timing of all of the RF being recreated. If you remember what it looked like from the beginning of the video series, there's our 4 channels of RF -1, the different pulse widths and periods, and we're going to zoom in now on both the spectrum frequency domain as well. So we're going to show you the timing of the pulses on the digital oscilloscope, and we're also going to show you some of the features of the spectrum analyzer function on the digital oscilloscope, but also some of those look a little bit better on an old school analog spectrum analyzer, so we'll show you some there too. Right now we're looking at the second channel with the 3 different linear FM chirps, and we're going to first start with channel 1. And that is a very simple pulsed CW with a simple fixed pulse width and period, no modulation, just right at the center frequency of 1200 megahertz. The second channel is the channel that had the exact same pulse width, 1 microsecond, but with 3 different chirp rates, so it has 3 different chirp bandwidths of 5 megahertz, 10 megahertz, and 20 megahertz, and you can see that in the spectrum display. The third channel, unfortunately, that's broken, was a binary phase shift keying one. We can't show you that, but we'll show you the 4th channel. And this was the one with the 4 different frequency shift keys off the center of -10, -5, +5, +10 megahertz. We're going to show you these on the analog spectrum analyzer in a second, because some of those looks a little bit better there. Okay, so we're going to move channel 1 from the digital oscilloscope and its mediocre spectrum display to an actual spectrum analyzer, and we'll show you some of the pulse parameters there. As you can see already, centered at 1200 megahertz, we have a typical pulse spectrum, and I'll just change the span to show that better. Keep in mind, it's a fixed pulse width, PRI, center frequency, no modulation, so you should see the perfect sine x over x sync function, with both the pulse width PRI and also the off time for the dwell showing up in there as well. So there's channel 1 with just pulse CW, fixed pulse width PRI. Okay. All right, so if you remember, channel 2 from the pulse setup was the same pulse width, but with 3 different chirp rates, and you can see that on the digital oscilloscope, and we'll show that to you on the analog spectrum analyzer. And with this setup, you can clearly see the 3 different modulation bandwidths for the 3 different chirps with 3 different start frequencies. I'll show you that just a little bit clearer if you watch. See how there's 5, 10, and 20 megahertz? 5, 10, and 20 megahertz filling in. Okay. Okay, so on channel 4, if you remember, this is the FSK, the frequency shift keying modulation, and you can see the 4 peaks in this spectrum, and we'll show it to you on an analog spectrum analyzer. Again, centered at 1200 megahertz with 4 different frequency offsets, -5 and +5 megahertz, and -10 and +10 megahertz. So we'll just max hold that, do a marker, and delta, -5 megahertz, sorry, +5 megahertz. 10 megahertz, -5 megahertz, -10 megahertz. And there's the 4 peaks for the 4 FSKs. Okay, so for tonight, again, we're only showing one major feature of the PDW2RF machine based on the RF SoC technology, the RF system on a chip. Again, we showed you the ability to use a PDW interface to transport it to our machine and parse through that interface and send all the commands to the digital analog converters to create the RF out of this machine, and our RF up converters can send it all the way out from 100 megahertz to 20 gigahertz. The important thing here shown tonight is the ability to faithfully recreate the RF that was created from someone else's thread emulator. It just so happens to be the Giga-tronics thread emulator. The idea here is if we can do it with our proprietary PDW interface, we can do it with your PDW interface. It's just a software application that does the translation based on your interface specification and your interface control document to our inputs to our FPGA that controls the DACs on the RF SoC card. So the idea here is if you want to recreate faithfully someone else's PDW interface, say CSIM or A2 paths or even Keysight UXG, if you could take those PDW streams captured or created, or if you're the one who actually specifies them, say for like a UXG, we can create the RF from that interface as well. If you have a lot of faith in your scenarios that you want to recreate on a little bit more compact and more affordable piece of hardware, come talk to us. Bring your PDW interface and your ICD, and we'll faithfully recreate that RF for you. And as always, we're what you would call professionals, so please don't try this at home.